Alright, this could be a tough one. So, the first thing I'm going to do is discuss the conjugacy classes of D8. And we'll first discuss the conjugacy classes of D8 using the following pictures. So what I'm going to do is there's 5 conjugacy classes of D8, and I'm not really going to prove that these are the conjugacy classes. Rather, I'm going to show you how you would find them and try to convince you that they are the correct conjugacy classes. But I think let's see, this problem says, let D8 be the dihedral group, so the symmetries of a square. I've also seen this exact same question posed, but it says you can use the fact that D8 is a square. Or you can use the fact that D8 represents the symmetries of a square. So I think this problem actually wants you to kind of do this sort of a discussion to explain why there's 5 conjugacy classes, because I mean, you could just symbolically prove that these are the 5 conjugacy classes, but it would be very, very time consuming, because you'd have to essentially compute every single possible conjugation and prove that these 5 conjugacy classes are indeed conjugacy classes. There could obviously be slicker ways of doing this, but anyways. So the way that I understand conjugacy classes is that they're sort of especially if we're discussing a geometric group, like a group that comes about that arises naturally in a geometric setting, then obviously it's like the symmetry. A group is like the typical example of a group is the symmetries of a particular shape. That means anything you could do, the collection of things you could do to a shape to preserve its order. And I've had conjugacy classes described to me as those particular actions, those particular symmetries, which you could identify even if you didn't have the beginning and ending, the beginning and ending positions. If you just saw the action, you'd be able to identify it. So, for example, by the way, the reason I'm doing this first is because I'm drawing a lot, and so if I were to do this later on, I don't think it would work. Like, my computer would explode. So, anyways, consider this one. We go from this square to this square. This is obviously this is a element of D8 because it's a symmetry of the square. But what have we done here? The way you get from this first square to the second one is that you just rotate it counterclockwise 90 degrees, or pi over 2. So what that means is that you have a conjugacy class of just things that arise as rotating by 90 degrees, either forward or backwards, because in conjugacy classes you also have the backwards direction. And so the thing is, it doesn't matter if you start with like 1, 2, 3, 4 here, or like any other indexing of these 4 corners. You can in any situation you can kind of see that going this way 90 degrees and going the other way 90 degrees. These are sort of the same thing, regardless of which position you're starting in and which position you're ending in. And if you were to do something like flip 180 degrees, like 1, 2, 3, 4, and then we're going to go to 1, 2, 3, 4, then sure, this is a group action, and you can get it by turning 90 degrees twice, but this thing itself, this cannot be represented as a rotation by 90 degrees. This is actually a rotation by 180 degrees, and that's really the only way to represent it. And so it doesn't belong to that conjugacy class. It's sort of it's almost a different category of symmetry of the square. And so I don't know if that's illuminating at all. It certainly is not mathematical. It's not rigorous in any way. But if you use those arguments, then let's see here, we have one that's the identity. Then we have one that's 90-degree rotation, and we can either rotate to counterclockwise or we can rotate clockwise. Then we've got the 180-degree flip. We'll just draw it going. Actually, it doesn't really matter because, pretty much wherever you start, you just flip it 180 degrees, and if you do that twice, you end up back where you were. So that's the only thing there is. That's the only element of this conjugacy class. Then you have the diagonal flip. So if you look at the diagonal here, then you could flip it along the diagonal. So if we have 1, 2, 3, 4, then this would go to, let's see here, the 1 and 3 would stay, but the 2 and the 4 would flip. And you should be able to see that this is, because we've completely switched, like if you're going counterclockwise around the square's vertices and labeling everything, you've completely flipped up the order that you go in. Whereas like the identity, 90 degree and 180 degree turns, those all preserve that order. And so you should be able to sort of intuitively see that this is a completely different type of symmetry than the other ones that we've seen already. And of course, how many of these diagonal flips do we have? We have 2 of them. Each one goes through opposite vertices. And there's only four vertices for 2 sets of opposing vertices. Then similarly, or lastly, we have, let's see here, where can I, I'm just going to call these mid flips for something very concise. But like you take the midpoints of 2 opposite sides and you connect them through a line and then reflect about that line. And so like that will send 1, 2, 3, 4. It will flip 4 and 1, and it will flip 3 and 2. And so again, this completely changes the order in which these indices appear if you go counterclockwise, and it is also different than the order that would occur if you were doing a diagonal flip. And how many of these do we have? We've got 2 of them, one for each set of opposite sides. And so how many actions have we described here? We've got the identity here, there's 1. We've got 90 degree turns, we have 2 of them. 180 degree turns, there's just 1. 2 diagonals and 2 mid flips. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 total actions, and this is a group of order 8. And so that means that we have exhausted all of the elements of the group, and so we have just 5 conjugacy classes. And so hence, D8 has 5 conjugacy classes. Now that is a really poor argument. It's really not mathematical. It's sort of neat. It's sort of interesting. Like you actually get to look at something. I'm personally very visual, and I like arguments like this. But you would, like, if you really wanted to convince someone of this, you would have to write a mathematical proof. And I don't know if there's an easy mathematical proof of this other than just going through and computing all possible, like, you know that, let's see here. So, let's see here. Let's start writing the next thing. We know D8 is the group generated by R and S under the relations that R to the 4 is equal to S squared equals E and SRS equals R cubed. So here, rotation, or R stands for rotation. So R is just a 90-degree rotation, and obviously if you do it 4 times, you get back to the identity, or you get back to where you started, and so you have the identity action. And then S squared is, or S is just 180-degree turns. No, is that right? I don't think that's right. No, S is one of these mid flips, I believe. Right, of course it has to be, because otherwise, if S was just 180-degree rotation, then it would be R squared, and then they wouldn't be adding anything else to the group. No, S2 is right, yeah, S2 is reflections. Yeah, rotations and reflections. So S is just a reflection. So it's a mid flip, and so you have that. And then, of course, if you rotate something 3 times, then instead, so that's like rotating backwards. And so what you would do is you would do a mid flip, and then you would rotate it, but then you would flip it back, and that would be the same thing as rotating twice, because let's see, if we had 1, 2, 3, 4, that would go to 1, 2, 3, 4, and then you this is R3, and then if we did S and 4, 1, 3, 2, then R, this is 1, 3, 2, 4, and then you flip it again, get 2, 4, 3, 1. And that is not right. That is not correct. That is not what I started out with. What would work here? Oh, wait a minute. No. It's I think okay, so this is the issue with the pictures. I think I should be thinking of the square like this. So that we have like one vertex at 1. And then so in this case yeah, and in fact if you had like a 1, 2, 3, 4, yeah, because this also has to work for odd order things, and so if you had a triangle, the only way to flip it would be to flip it here. Like you wouldn't be able to do this mid flip thingy on a triangle, which had an odd number of sides. And so what this really has to be is the diagonal. And so let me erase this. By the way, this is not how you would do this problem on a test normally, or like just anything in general. You would not want to be doing this. So this is R3, and then if we had 1, 2, 3, 4, then we rotated it. No, if we flipped it, then we'd have 1, 3, 4, 2, and then we rotate. That would give us 1, 4, 3, 2, and then we flip back, and that gives us 2, 4, 3, 1. And look, these two things are equal. So yeah, there we go. So you should really be thinking of squares as diamonds so that it hits 1. And then, so then R is rotation by 90 degrees and S is reflection across the x-axis, which if you're thinking of it as a diamond, is actually corresponds to this diagonal action here. So anyways, why did I go, I jumped ahead and wrote it this way. For a reason. I wanted to finish up something about these conjugacy classes, I think. But anyways, we have these 5 possible conjugacy classes. And so we get 8 elements, and there's only 8 elements in our group, so we're done. So again, hopefully you don't have to just be like, oh, these are the symmetries of the square, and so we have the identity, 90-degree things, 80-degree things, diagonal flips, and should call this more like vertex flips and midpoint flips, because then it corresponds with the actual picture of, you know what? I'm just going to go ahead. No, my diamonds. I can't draw diamonds for some reason. Squares are alright. Diamonds not so much. Pretend that's a diamond. Then, lastly, we have these midpoint flips. Okay, so there we go. So now it looks like the way it's actually supposed to look like. And so yeah. So those are the conjugacy classes, and you should, maybe if you can just, if they allow you to be like, oh, these are the symmetries of the square, then you can be done. Hopefully that's good enough, but it might not be. But anyways, we know that this is what D8 is. This is just, we learned this like very early on in group theory. Okay, so consider the subgroup H, which is just E and R squared. This is obviously a subgroup of D8 because, let's see here, if you take R squared and multiply it by itself, you get R to the 4th, which is just E. And let's see here, then H is normal in D8. And why is that true? Well, you can sort of, if you want to, this group's small enough where you can actually conjugate it by everything in D8. Well, obviously, if you conjugate E by anything, you're going to get E. And so, that's obviously going to work. But what you have to do is you have to conjugate R squared by every element of D8 and prove that you either get R squared or E. And that's only 8 computations, so that's not a lot. But I don't want to do that right now. I mean, I could, obviously. But it just seems like a lot of work for something that either there should be some easy way. I'm going to try to fix some of these. There should be some easy way of doing it. Or you're allowed to just use a geometric argument. And if we were allowed to use a geometric argument, we could just say, hey, look at these conjugacy classes. We have this 180 degree this 180 degree rotation is in its own conjugacy class. And if you, let's see here, the subgroup that it generates is just E. And let's see here. So it's in its own conjugacy class, and so conjugating by it is going to just give you it or E, And so you should be able to argue just because it's in its own conjugacy class that H is a normal subgroup. So I'm just going to leave it at that. If you want more details, you can actually compute it. So now that finishes up the really like strange stuff in this proof, like the stuff that I don't quite know what the best way of presenting is. Certainly, if I were on I'm not quite sure what the best way of presenting it. That might just be something that you're supposed to know at this point. But anyways, let's keep going. So since norm of H is 2 and D8 is 8. By the way, why are we... Oh, here. Then I'm going to finish this sentence and then ask this question. So D8 set minus H... No, mod H is 4. So what are we doing with H? Why are we finding a normal subgroup? What we want to do is we want to get a normal subgroup which has a... We want to get a quotient group that has a character table which is really easy to write down, and then we're going to inflate that character table to get the desired character table for D8. And if you don't know how inflation works, it's there's not much to it, but for some reason Sayre's textbook I don't believe discusses it, but you should be able to find it in... There's got to be some textbook out there where you can find inflation. Okay, but anyway, so D8 mod H is equal to 4. So this D8 mod H, that's going to be the subgroup that we're going to write a character table for. See here. So it's of order 4. So what do we know? So D8 mod H it's either isomorphic to C4 or D8 mod H is isomorphic to C2 cross C2. Let's see here. So let's consider two elements of this. So one element we have is R squared times H. And what happens if we multiply that by itself? Then we get R to the 4th H, which is just H. And what about S? S squared, this will just give us S squared H, which is equal to H. And so, what does this tell us? This tells us that D8 mod H has two distinct elements of order 2. And so D8 mod H is equivalent to C2 mod 2, or C2 cross 2. And that's because C4 you've got, you think of it as being the moduli classes of, you've got 0, 1, 2, 3. And 1 and 3 both have order 4. 0, no one cares. And then 2 has order 2. Well, obviously 0 has order 1. But, yeah. 2 has order 2. And so you've got, if in C4 you have 2 elements of order 4 and 1 element of order 2. Whereas in C2 cross C2 you've got 1, 0, which has order... Yeah, you have 1, 0, which has order 2, and 0, 1, which has order 2. And so you have 2 distinct elements of order 2. And that differentiates C2 cross... That's one of the things that differentiates C2 cross C2 from C4. And so, anyways, we have this isomorphism here. So, also, C2 cross C2 is abelian. Right, C2 cross C2 is abelian. So what do we know about, so now let's actually start thinking about things that could help us make our character table. So we want to know about representations. So we have an abelian group, and so all irreducible representations of D8 mod H have degree 1. Let's see here. So then we begin our character table with, right, let's scroll down a bit and draw it out. So, I'm going to need some space for this. So we have chi of theta 1, chi of theta 2. Okay, so let's start with, we have some conjugacy class here. Let's just call this E, and this is going to be, let's see here, E of D. Let's call this, let's see, we're using H. Let's call this K. So we're going to call this E sub K. So this is the identity in K, which is D mod H. Oh wait, no, that's just H then. Okay, so let's not use that. So we always have one conjugacy class that's just this, and we know that this, if we go down, we have N1, N2, blah, 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 and these will give us those are going to be the degrees of the irreducible representations of our group. So let's see here. D mod H has degree 1. Or no, D mod H is abelian, so all irreducible representations have degree 1. So every single Ni is going to be 1. So this is just going to be 1, 1, blah, blah, blah. Now, how big is this? How many rows are we going to have? So then, because, and we're going to recall this fact, the order of G is going to be the sum from 1 to m of Ni squared. Our character table starts with this. So we have the sum of the Ni squares has to be the order of G. Well, D8 mod H is, the order of D8 mod H is 4. So actually let's write in D8 mod H here. So the order of D8 mod H is 4. That's like the first thing we discovered about D8 mod H after discovering that it exists. And we also know that because all the irreducible representations have degree 1, that each Ni is equal to 1. And so we need to find this m here such that all of these Ni squareds sum up to 4. So you add up 1 to itself a bunch of times and you get 4. So that means that we're just going to have 1. Or that means we're going to have 4 rows. So let's see, we're going to have, let's say chi theta 1, theta 2, theta 3, and theta 4. So these 4 are our irreducible representations of D8 mod H, and these chi's are the corresponding characters. And so we know that there are exactly 4 rows here, and we also know that the number of characters is the same as the number of conjugacy classes. And so we're going to have, going to call them C1, C2, and C3. And actually, it's very easy to see what these should be. We're going to have, one of them is going to be 1, 0, one of them is going to be 0, 1, and one of them is going to be 1, 1. because those are really the only conjugacy classes you can have. But oh, well, of course that's the case, because this is an abelian group, and in an abelian group, every single element is its own conjugacy class. So then that's another reason why you should know that there's 4 conjugacy classes, is because it's precisely the order of the group. And that also corresponds with some of the NIs. Yeah, so this stuff is all connected. Well, not topologically connected, but it's all the things are related to each other. Okay, and chi theta 1, we're gonna always assume that the first row is our trivial character, and so this is going to be 1s all across. Okay, so then our character table starts with this, and the rest is filled in using the formula. Let's see here, the sum from 1 to 4 of chi I g chi I g prime conjugate equals the order of, actually, yeah, let's write this the way that it would look for this problem. Theta I and chi theta I of g prime is equal to the order of D8 mod h divided by the order of the conjugacy class of G if G prime is in CG and 0 otherwise. So if you have 2 elements of our group, G and G prime, and G prime is not in CG, G prime is not in the, if CI is not in the center of G, or the conjugacy class of G, then, was that the same? I think it's the same. Not quite, but sort of. It's abelian, so it turns out to be the same. But because of this, we have this formula. So now what does that mean? That means that this basically means that the columns are orthogonal, and if you take the dot product of any 2 columns, it's going to be 0. And if you take the dot product of a column with itself, it's going to be the order of the group divided by the number of elements in that conjugacy class. But we know that each conjugacy class has just 1 element, and we know that D8 mod h is equal to 4. Well, D8 mod h has order 4. And so any column dot product with itself needs to give you 4. And so, well, of course, it's not quite the dot product because you're conjugating one of them. But anyways, yeah, so this is, so when you do that sort of dot product, what is that? Is that just, yeah. So that'll give you that. So anyways, we know that if we take any column and dot product it with itself, then it needs to give us 4. And so of course that works with the first column because you just get 1 plus 1 plus 1 plus 1, which is 4. And so it should be pretty clear how to do the rest of this table. It's pretty simple. You just use 1s and negative 1s. So negative 1, negative 1, negative 1, 1. And I don't think this needs much, it doesn't really need much additional argument because it's pretty obvious that if you take any 2 of these columns and do this dot product with each other, but with one of the columns being complex conjugated. Well, the complex conjugate isn't going to do anything because these are all real numbers. But then when you add them up, if they're different columns, then you're going to get 2 of them are going to become +1, and 2 of them are going to become -1, and then you add them all together and it gets 0. But then if you take any column and you add it to it, or you do that conjugate dot product to itself, I think, isn't that just like the typical like inner product by whatever it is. I'm not thinking functional analysis right now, but this is just a typical like inner product. But anyways, so you if you do anything and dot product it with conjugate by itself, then you're just going to get all everything's going to be squared. So you just get 1 + 1 + 1 + 1, which is 4, which is exactly what the formula tells us. So this is our character table. Okay, so that's that. And so now, since we know that D8 has 5 conjugacy classes, we can inflate the above table to get, and basically what inflation does is if you're modding out by a normal subgroup, then you can take this character table for this quotient group and just sort of copy and paste it into the beginnings of your next character table. So anyways, so let's see how that works. So we're going to start with E, and we're going to call that C1. Then we've got C2, C3, C4, and C5, because remember there are 5 conjugacy classes. Then we're going to call them Chi1, Chi2, Chi3, Chi4, and Chi5, because the number of characters needs to be the same as the number of conjugacy classes. Okay, so now right here is where we copy and paste the one that we were inflating. Come on, eraser work. God, this is going to kill my computer. My computer is bad enough already. Like, it just, I can't open internet browsers anymore. Like I open a browser and it crashes. Also, the computer doesn't record sound, so thankfully my phone still does, but I can't use that to sync up the audio and the video. And so, like, I have to sort of do some other things to check that things are in sync, and so this video might even not turn out very well because it might be it might not be synced properly. Is that what the if you take sync, what's the past tense of sync? It's not sunk, because it's SY and C. Anyways, so then, okay, so E, this is going to be the trivial one, so this is going to be N1, N2, N3. Do we automatically start with that? This is going to be N1, N2, N3, N4, N5. Yeah. That's part of how inflation works. Is that not only do you have this some conjugacy class here that corresponds to what was the trivial conjugacy class. Oh, well, this would have to be the one that you modded out by. No, but sort of, whatever it is. This, so you get this one here, and then this, I believe, just starts out automatically. You have ones in here. Right, because those were trivial. These are inflated irreducible characters, and yeah. So you just get to start with these. Then you have N5, and then let's call it B. No, I'm gonna write this as A because that's what I called it in my notes. So A, B, C, D, E. And we have to figure out what these are. See here. 8 equals the order of D8, which has to be the sum from 1 to 5 of ni squared, which is, we know the first 4 are 4. This is plus n5, well, n5 is just a, so plus a squared. So what is a? Well, so a squared equals 4, so a equals 2. Okay, so we have that. To find B through E, we compute. So here we use the orthogonality of the two of pairwise orthogonality of columns, and we're going to compare with. We now know what column 1 is. So 0 is, let's see, we're going to do 1, 1, 1, 1, 2, because that's our first column. I'm going to take the dot product with the second column. 1b. So that's 4 plus 2b. So then 2b is negative 4. And so b is negative 2. And we just do this with the other ones. And of course, the complex conjugates don't really matter because all these numbers are real. Well, actually, we can just take... Well, this first column is, they're real, so you can just take this one to be the one that we've done the complex conjugates to. But it doesn't matter. So anyways, we have 1, 1, 1, 1, 2. Then we do 1, negative 1, C. So this is just computation. I've tried to avoid a lot of computation in this problem, but there's only so much you can avoid. Okay, so anyways, these cancel out, and so you get C is 0. But now you should see, oh, shouldn't that happen for every single one of these? Because you're doing that you're doing that direct product, and the first 4 these first 4 terms are always going to cancel out because you're going to get 2 of them are 1 and 2 of them are negative 1, and so they're 0. And we know that because we did that exact same computation previously. And so yeah, that's what happens. So and likewise, we have D equals E equals 0. Hence, the character table for D8 is given by, and let's see here, if I scroll down enough, hopefully it will have refreshed enough. So we're going to have chi1, chi2, chi3, chi4, and chi5. I'm going to have E, which is C1, I'm going to have C2, C3, C4, and C5. Then we have 1, 1, 1, 1, and A was 2, 1, 1, 1, 1, and then this was minus 2. Then the other ones, we just had this character table, which was inflated, and then we had zeros down here. Okay, so that's our character table. I apologize, some parts of this video were pretty rough, and like especially the way that I started out this video, I didn't really give a proof that there are only 5 conjugacy classes of D8, but hopefully it's enough to where if there's anything that you aren't fully convinced with this proof, or anything that you like, you either think could be done better, or things that you saw it and thought, oh, maybe that's not right, there could be something wrong there. Hopefully there's enough in this that you can go back on your own and figure out like a nice, neat, ironed out proof. Although given how many details are in this proof, I don't think there's a nice, neat way to do this. I think no matter how you want to approach this problem, you're always going to end up doing some amount of calculations and just sort of having to get your hands dirty. But however you want to do it, and whatever way you'd like to do this problem, this should at least be a start for you, and hopefully it sort of sheds some light onto the process of finding character tables in the first place. You try to find a subgroup using typically using quotients. Like you find a quotient, you use quotients to find a subgroup, and this subgroup hopefully is something that's easy to work with, and then you get that character table, and then you inflate it, and then you just use the things that you know about character tables to fill in the rest. And so there you go, we're done.